We have been exploring the nature of the quantum states, especially in this Dirac-Bra-Ket formalism. And we talked about multi-particle states, etc. And we're primarily focusing on polarization of a single photon, and our Hilbert space is two-dimensional. We want to now talk about how do we look at transformations of our states. How do they change? Can they change? And this is a critical aspect of quantum mechanics, and it will introduce some new mathematics that we have to deal with in later lectures. But first, let's consider a simple example. I want to kind of just think of taking a single photon, and we'll set it up that the photon is in the plus state. Now, remember what that means. That means with our canonical coordinates of h and v, that we can set that. Again, it's arbitrary the direction, but we set h and v. The plus state is rotated 45 degrees, plus 45 degrees from the h state. So what it might look like, so again, just a physical picture might be a photon coming in. The polarization is at, looks like, 45 degrees to the vertical or to the horizontal, of course. And then we let it impinge on a Polaroid that has its orientation in the h direction. And that's how I'm representing that. That's the optical transmission axis. And as we know, if this is in the plus state, as it passes through, it will only send through an H polarization. And we know from the structure of our states and what we discussed before and our and everything else is that the state will be horizontally polarized, but the probability that it actually passes this Polaroid is 50%. And that's because we have our square root of 2 here of h and v. So h is the top one, v is the bottom one. The 1 over square root of 2, when we square it, we end up with a half. And we know that. So that's we're going to take that as clear and unambiguous. So that tells us that after the state here, it's not actually h. Now, we're considering the whole system here. So we're talking about from the beginning of the experiment, which is going to be starting with this state, we're going to have 1 over square root of 2. And the reason is because we are filtering out half of them, but the state changes to that. And we can think of that, let's get rid of this, as follows. The state goes from the plus state to the h state, just as we said. And all it does is it selects out the 1 there. That's all it does. Now we can think of this is where we're going to get into this. The transformation represented a matrix acting on our column vector as follows, this. And here is what we think. And when we think about it, it's pretty obvious what this should look like. We just have a 1 with everything else being a 0, and we do the matrix, we can forget about the 1 over square root of 2. We get 1 in the top, and then we get 0 on the bottom. So just all this operator here does is factors out, or filters out, or what we call project. That's going to be the word we're going to use later. Projects out the horizontal component of the state. So this would be, we could call it psi after in terms of that. Now, we represented this in terms of a matrix. And remember, when we do our matrix representation, it is basis dependent. So really kind of our HV basis is our canonical basis. We're choosing it as 1, 0, and 0, 1. And then the other ones follow. We could choose different ones, but that's where we're choosing. But there is another way to do it that does not depend upon the basis chosen. And that's using our Bra-Ket formalism. And there's a way to represent this purely in terms of our bras and kets. And that's going to introduce the next mathematical form we need. And it's called the outer product. Now remember, we took the inner product of a bra acting on a ket, and we thought of it, remember, that's the analog of the dot product. The outer product is a little different. It's actually a ket vector times a bra, the reverse order here. So if we think about this quantity here, h ket, h bra, remember the order depends, acting on our initial state, which was plus, notice what it does. This is an inner product that gives us 1 over square root of 2 when h acts on plus. So that's where this comes from. And then afterwards we have an h. So this is what we call an outer product when we write it like this. So again, it's in reverse order of ket bra as opposed to bra ket. And it is an operator. Notice what we have. We input a vector, which is the plus. We output a vector, a state vector, if you will. So So it's a different type of operation than inner product. Inner product is you put in two vectors, you get out a scalar. Here you put in a vector, you get out a vector. And this one just projects out the h component of whatever was in the initial state, which was plus. So that's hopefully pretty straightforward. The mathematics should be simple, but we have to get into a little bit more and learn a little bit further more about this. So again, we said we can call h acting on h. That's an operator. That entity there is an operator, and it projects out the h component. The v projector projecting out the v component is simply going to be v on v. That should be obvious. But let's take a look at what that matrix looks like. Now, an operator, what we're saying here is when we have an operator, we can represent it as a matrix. And let's look at what that v, it's just simply going to be that. Because if we go back to that plus state, it's pretty obvious that it's just going to pick out the lower part of that vector. So it's pretty straightforward. But one thing that's important here, notice that there's a relationship between the h projector and the v projector, as I'll call it. And if we add those projectors, remember they're the two basis ket vectors in this orthonormal basis of HV. If we add them, we get the identity operator. Remember, the identity operator is just the ones on the diagonals and everything else is 0. That's the matrix that does nothing to a vector, or column, row vector, whatever, or another matrix. It just keeps it the same, the identity, the equivalent of 1. So if we perform, and so this is important, is that if we take a particular orthonormal basis and we add up these projectors, all of them, it'll equal the identity. And that's an important relationship. And it's important to understand why, because if you think about it, if we perform a measurement in the HV basis, you're either going to get an H or a V with probability 1. And the probabilities add up to 1, so that's essentially why we're getting a 1 there, if you will. Okay, now let's formalize this a little bit. This is called the resolution of the identity. And what it means is that, well, if you take an orthonormal complete set of basis vectors in some Hilbert space, so it spans it, that's what we mean by complete. So there's going to, in an n-dimensional Hilbert space, there's going to be n vectors. Again, think of these as unit vectors if you want to kind of have a comparison to our old classical physics. So we need the same number of unit vectors as the dimension of the space. But if they're orthonormal, then when we add them up, we get the identity operator. Now, this comes useful in many ways, which we probably won't exploit in this course. But it allows you to take a particular state and then kind of transform it to any basis you want based on this. You just multiply by 1. And as long as you select the basis that you want to expand it in, that's all you need to do. So it's a useful tool to analyze the kets. Okay. Now, let's go on. Let's do some examples. And I think it's useful to understand this in terms of examples. Let's continue to talk about polarizers. So let's say we have some state. Let's start with an H. So it's polarized. We prepare a state so it's H. We could do that with a polarizer, if you will, set in the H, and we just take that light coming out. Think of it as a series of photons. And we want to send it through a bunch of polarizers, one after another. And we'll put them in this order, plus, R, H, minus. Again, what we mean there is it's going to go through the plus 1, then the R, then the H, then the minus. Just quickly drawing that out. So we would start with an H polarized photon. And then we're going to send it through a plus polarized, which is plus 45 degrees. Then we're going to send it through a right circular polarizer, which I'm going to represent like this. And then we're going to send it through an H polarizer. And as we know from our optics course, we're going to get something out of here because none of these none of these directions are orthogonal in sequence, which is important. So this would be minus in that direction. And then we want to see what we're going to call psi after. Like that. So that's how we're going to carry this out. Now, let's Okay, and the question is, how do we represent this? Well, we do it with a series of operators acting on our initial state, which is h. So let's take a look at it. And it looks a little cumbersome, but just examining it should be clear. So again, notice the direction that we work in the opposite order. This is the way our operators and kets work. So we start with the beginning operators h, then we send it through a plus, so this is the plus projector, if you will. Then we send it through an R, so we slam on the R projector, and then we send it through an H, we slam on the H projector, and then we slam on the minus projector. And all this whole term gives us what we're going to have afterwards. So let's go ahead and calculate it out, see what we get. We have all the vectors up here, so we can actually carry this out very easily. We have a series here. Now notice, so let's just go through these in turn. H plus, or plus on H, so we look at those. Well, we're just going to get a factor of 1 over square root of 2. R on plus, this one's a little non-trivial, and I'll leave it to you to verify. But if we act on this one, well, actually it's the next one, I should say. The R on plus, this one. Notice we're going to get 1 and 1 on I. So that's where, and a minus because this is a bra. So that when this becomes a bra, that becomes a minus I. It acts on this one here. So that's why it's 1 minus I over 2, because we have the 2 squared. So that one's the non-trivial one. Then we go from H on R. Well, again, that's just going to be this on this, which just pulls out a 1 over square root of 2. And lastly, we have minus on H. So we look at that. On that, well, again, we just pull out a 1 over square root of 2. And putting it all together, we get this, 1 minus I over 4 times square root of 2 times minus. That's the state after it goes through our polarizer. And of course, now you can ask a question, what's the probability to measure the outcome minus? So let's just do that. And what we do is, recall how we do this. We want to find the outcome minus when it's in the state psi after. So we slam the bra on that one, take the modulus square. And again, it's just going to be this, so minus on minus, that's trivially gone. So 1 minus I over 4 square root of 2 modulus squared. 1 minus I modulus squared is equal to 2. You're going to verify that because it's 1 minus I times 1 plus I. And then the bottom square turns out to be 1/16. And you could probably remember this going back to your optics course. That remember that the first one cuts down to half, the next one another factor of 2. So we're going to have 2 to the 4th, 1 over 2 to the 4th, which is 1/16. So it's consistent with what we anticipate knowing the property of our polarizers. Okay, let's look at another example. And let's talk about the general state. This is the most general state we can write in a two-dimensional Hilbert space. Again, we have the angle in the two-dimensional, and we have the phase factor here because it's a complex vector space. But we just want to know what happens, say, we send this through an R polarizer. And then we want to find the probability for it to be measured. So our answer is going to be in terms of theta and gamma, of course. But let's go ahead and do this. This one turns out to be a little bit involved, but we'll go through it in turn. So again, the probability to R in the state psi, so we just stick in the psi here. We slam the R through, so again, the cosine and the sine, those are just functions. So it's R on H and R on V quantity squared. Let's act on that. So what we need to do is find R and H, which again, we go up here, and that's just going to be 1 over square root of 2, so that's pretty simple. And then R on V, that one's going to pull out an I, because there's I in the bottom there, clearly. So let's go ahead and carry that out. So this is what we get. So we get 1 over square root of 2 for R and H, and we get minus I over square root of 2 for this one. Notice the minus I is coming because of the fact that the R is a bra. We take the modulus square of that. We clean it. We're going to pull out the factor of 1 over square root of 2. We're squaring it. So that's cosine theta plus, and I took the minus I and turned it into a minus pi over 2 here. So we're switching the phase a little bit there just to make the math a little bit cleaner. Now we square it out. And so notice the end terms, cosine squared and sine squared, this will be either minus I that and either plus I that, so we just get cosine squared plus sine squared. The cross term is going to consist of a cosine and a sine, but these two exponentials, but with the signs different because one's modulus squared. Or one's complex conjugated. But remember, you should know this, and this is a form of a cosine, up to a factor of 2. So it's 2 times the cosine. So this is simply 2 times the cosine of the argument. So we put that here, and this is our result. We could clean up, well, that's actually pretty close there. But that is a general answer here for measuring right polarized photon when it's in this state, what's general state. And of course, it's going to depend on theta and gamma. Okay, so that's a little more non-trivial example. You probably want to go through and review it if it's not clear. But let's go on, and let's talk about more of these operators. So we're going to introduce some. There's a small number that we need. And again, if we want to talk about quantum information, cryptography, or computing, we need these small number of gates. These are what we call single qubit gates because they only act on a single object. Later we'll talk about a small number of 2 qubit gates. But we're going to list this out. Again, we're going to put them in when needed in the matrix form just to tell us. But the first is the identity operator, which is pretty trivial. It does nothing to the state. So we can think of it by what we introduced, the resolution of the identity. We can represent it in many ways as in the H bases, in the plus PM bases, we'll call it, in the R bases, and in general for some angle theta, without the gamma there, as long as this one's perpendicular to that one. And again, it's all going to be 1, 0, 0, 1 in this case. The matrix is going to look the same. So the identity does not change when you go to different bases, because it doesn't do anything. The next one, which we're going to come back to look a little bit later, is we'll call it the swap operator for now. Some people call it that, but really X is what we're going to call it. And there's a reason why. It's convention, of course, but what it does is it swaps H and V. So here's where you can learn how to write these outer products, and it's actually a nice scheme to do this. So this is what the operator looks like. There's 2 terms, but notice what it is that this, we look at this first term, this one acts on the input vector. So this is the input. So if you input V, this is what it returns, H. So remember, V on H will die, so this takes the V and spits out an H. This one takes in an H and spits out a V. So it swaps it. And simply, that's just the off-diagonal one. You can quickly verify it by yourself if that's indeed the correct matrix representation by changing because of our simple structure for H and V. Let's take a look at what happens with this particular operator in the PM bases, the plus-minus bases. This is of interest, so we'll come back to this shortly. So let's just act on it. And so let's do the plus first, do it slowly. So X acting on the plus one. So here's our operator. I factored out the 1 over square root of 2 just to keep it simple, and that's 1, 1 is the plus vector. But notice what it does. It just interchanges these two, which is still the plus vector. So it takes the plus vector and returns the plus vector. Doesn't do anything to it. What does that mean it's the identity? No, because when it acts on the V, notice what it does. Again, now it flips these, but since it flips these, that's equivalent to be the minus of that. So it pulls out multiplies by a factor of -1, if you will. So the action of this X operator is different in the PM basis than it is in the H basis. Okay, lastly, let's put one that will be of interest later. It's called the Hadamard gate. And what it does, it converts a vector that's in the HV basis to the PM and back. We can just quickly look at its action. The operator looks like this, 1, 1, 1, -1. And I'll let you verify this. It's really easy to do, just some simple multiplying of this with the vectors that we had before, with the column vectors. That it takes an H and it returns a plus. Acts on a V and returns a minus. It takes a plus and returns an H, and it takes a minus and returns a V vector. Pretty basic. And this is useful in quantum computing. The Hadamard gate is an extremely well used and often used vector in quantum computing. Okay, lastly, we need to get to the important aspect here, the more mathematical aspect. And we want to kind of consider these operators of a particular form, that do a particular thing, I should say. Okay, now we want to consider these operators acting on particular states, but we want to consider a class that are special. And they are really special in quantum mechanics, but they are ones that take the operator and doesn't change the state. So if you input, say, an H, it returns an H up to an overall constant. The constant we'll discuss in a moment. So let's consider an example. Now, to do this, what we need to do, which we haven't done yet in our polarization bases, is to come up with a convention to quantify the outcomes. Right now, we've been calling H, V, R, L. We need something that's better than that. We need a quantitative measure. So, for example, if we're talking about position, we can say, oh, it's 3 meters versus 5 meters, etc. And it's quantified. Our outcomes are quantified by the real number line. we need to do the same for our polarization outcomes. So what we're going to do is the standard convention, and actually is very useful, is we're going to call them plus minus 1 because there's two possible outcomes. Now we could call them zeros and ones, especially that happens if we're going to be doing quantum computing later, but right now it's easier to understand it in terms of plus and minus 1. And the convention we're going to choose is the following. So in each basis, one outcome will be plus, the other one will be minus. So in the HV basis, we'll call, if it's an output in H, we'll call that plus 1. If it's a V, we'll call that minus 1. The PM basis, pretty simply, plus will be plus and a minus will be minus. And the RL basis, R will be plus 1, L will be minus 1. And you could think of that as a convention, but it's consistent and it makes life easy, if you will. But what we want to do is have a operator that spits out the same. If we take, in a particular basis, if we input one of the basis vectors, it returns the basis vector, but multiplies it by its outcome, plus or minus 1, corresponding to it. And this will be an extremely important one. So, and we multiply by the outcome, that's what we said. And such an operator is called an observable. And really, we're getting at statement of the postulate 2 in our earlier discussion. Okay, so let's do this for the HV basis, where it turns out to be very simple to construct the operator. And once you kind of see how it works, it's actually very easy. At least in this case, this polarization case. So we're going to call it, now again, this is just a, we don't have a really good name for it, but we'll call the operator O. And again, we're going to use this caret on top to indicate that it's a operator. This is often done in introductory quantum mechanics courses by using a caret over it to indicate it's an operator. Later on, when you go to more advanced courses and you start using quantum mechanics, you'll remove that crutch and that caret won't always be there. So we're going to call it O sub HV. So it's the observable for the HV bases. Now, we're also called Z. And the reason is because that's what it's called in the, well, in the quantum information community, but also if we do this in terms of spin, this would be corresponding to Z in the spin in the Z direction. So that's why it's called Z. So it's this convention, if you will. We'll start calling him by Z later. But right now I just want to kind of think of this in general. But to construct this, remember what we do. We want to kind of take one of the basis vectors in, return the same basis vector, but multiply it by its numerical quantitative outcome. So H is plus 1, so we simply take H on H and put plus 1, and V we want to be minus 1, so it's minus V and V. So clearly, now that it should be obvious now that if we input an H, we're going to get plus H. If we input a V, we're going to get minus V. And the operator looks like this, 1 minus 1 on the diagonal. So we can go for our other two complementary bases. Let's take a look. For PM, we'll call it X. And again, remember, we already did this in the previous screen. If you remember, it's just the swap operator. And again, how do we construct it? Well, we just do plus, plus, and then minus, minus. And you can go through the algebra. It's very easy to show that 0, 1, 1, 0, even though we showed it in the previous screen, that is indeed the operator. So this is the observable for the PM for polarization in the PM bases. And again, we're using our canonical form for the matrices where H and V are 1, 0, and 0, 1. Lastly, for the RL basis, again, we can, and then we're going to call that the Y, so it's X, Y, and Z. There's a reason for that because of the spin. We just say R, and we subtract L and L because those are the eigenvalues that we're going to come back to. I'll introduce the terminology in a moment. But if you construct that, it's not hard to see. Just go back to those row and column vectors, that it's 0, minus I, and 0. Now these set of three matrices, and including the identity, forms a group which is rather important in most of quantum mechanics, called the Pauli spin operators, but we'll not burden ourselves with too many names and terminology. But I do want to get to the terminology of this construct of these observables. So let's just consider a general case, and what we mean by this is we have some operator acts on a basis vector or a vector, or state vector, and it spits out the value of corresponding to that and that. So in this case, we would have some observable which is represented by O. Let's get the names down. And what it does, it returns this value, the outcome value, omega sub I in red, and we call that the eigenvalue. This is from German, and there's reasons historically why this is called that. The vector which corresponds to that eigenvalue is called the eigenvector, and it corresponds to some observable O. So in this case, we think of this state, omega I ket, if you will, as representing a state that has a definite value of omega I of this observable O, which has a range of outcomes. And this is kind of the critical expression in quantum mechanics that is dealt with, is eigenvalue, eigenvector correspondence, if you will. Now let's just tie up some things. Let's ask a question first. So is H an eigenvector of X? So recall, X was the observable for the PM bases. Is H an eigenvector of that? And you should be able to answer that right away. And the answer is no. Really all you need to do is plug it in and show that if you act X on H, we flip it to V. So it's not an eigenvector because it's not the same vector. It has to be the same vector up to a constant or function attached. Okay. Lastly, we note that because we're talking about, or actually, before we do that, let's say the photon has a definite value in the HV basis. That's what we mean here. It does not have a definite value in the PM basis, or vice versa. That's what we mean by that. And lastly, since we're talking about observables, physical observables out in the real world, all of the properties we measure have outcomes, quantitative outcomes that are real numbers. So that means that whenever we talk about our observables, the outcomes are real numbers. Thus, the eigenvalues of our observables must be real. And that's a constraint that's going to limit the range of possible operators that can represent physical observables. That the eigenvalues have to be real. Okay, this is to get us going in it. We'll talk about particular types of operators in the next lectures, and we will get into this, and now that we almost have the entire mathematical formalism at hand.